Ever wondered how the quality of software is measured? In the vast world of software development, we have a tool at our disposal known as software quality metrics. These are measurements that assess the quality attributes of software products, processes, and projects. Much like a magnifying glass, these metrics allow us to closely examine various aspects of software quality. They give us the power to quantify these elements, which in turn helps organizations spot areas for improvement. Think of software quality metrics as the compass guiding a ship. It helps navigate the complex sea of software development by providing valuable information. This gathered data assists in making informed decisions that can significantly improve the overall quality of a software product. From measuring the density of defects to assessing customer satisfaction, these metrics come in many forms. So, without further ado, let's dive into some common software quality metrics. Firstly, we have defect density. This crucial metric is all about sizing up the number of defects identified in a software component or system and dividing it by its size. Think of size in terms of lines of code or function points. The purpose of defect density: it's a reliable way to measure the quality of software code. By assessing the frequency of defects relative to its size, we get a clear picture of the code's quality. The formula is quite straightforward. Defect density equals the number of defects divided by the size of the software component. So if you find yourself with an unusually high number of defects in a relatively small component, you've got high defect density. And remember, in the world of software quality metrics, less is more. So the less the defect density, the better the code quality. Next, let's talk about failure rate, mean time to failure, and mean time between failures. Failure rate is a metric that measures the frequency at which software components or systems fail or experience errors during operation. It's essentially a ratio that compares the number of failures to the total usage time. So, if a software component fails 5 times over 100 hours of operation, the failure rate would be 5 over 100. This metric is incredibly important because it provides insights into the reliability and robustness of software products in real-world usage scenarios. Next up is mean time to failure, commonly known as MTTF. This is the average time between the occurrences of failures in a software system. It's calculated by dividing the total usage time by the number of failures. For instance, if a system runs for 1,000 hours before experiencing 10 failures, the MTTF would be 1,000 divided by 10. MTTF is a critical measure of the reliability and stability of software, as it estimates the average time it takes for failures to occur. Last but not least, we have mean time between failures, or MTBF. This is the average time between consecutive failures in a software system. The formula for MTBF is the total usage time divided by the number of failures minus 1. So if a software runs for 1,000 hours and experiences 10 failures, the MTBF would be 1,000 divided by 9. MTBF provides insights into the frequency and intervals of failures, helping assess system reliability. It's important to note that these 3 metrics, failure rate, MTTF, and MTBF, are interconnected and often used together to provide a comprehensive picture of a software's reliability. They allow us to understand how often failures occur, how long it takes for them to happen, and the average time between them. By monitoring these metrics, developers can identify patterns, predict future failures, and ultimately improve the overall quality of their software. These metrics together give a comprehensive view of software reliability. Now, onto code coverage and cyclomatic complexity. These 2 metrics are crucial in evaluating testing efforts and quantifying code complexity, thereby enhancing the software's overall quality. First, let's talk about code coverage. It refers to the percentage of code lines or branches that have been covered by automated tests, such as unit tests or integration tests. The purpose of this metric is to evaluate the effectiveness of the testing efforts. It also helps identify areas of code that may not have been adequately tested. The calculation is relatively straightforward. Simply divide the number of lines or branches covered by tests by the total number of lines or branches in the code, then multiply the result by 100%. This gives you the code coverage percentage. Now let's move on to cyclomatic complexity. This metric measures the complexity of software code based on the number of linearly independent paths through a program. It provides a quantifiable measure of the structural complexity, which can be crucial in assessing the maintainability and testability of the software. The calculation of cyclomatic complexity is derived from the number of decision points in the code structure, such as loops and conditionals. A higher cyclomatic complexity value indicates a more complex code structure, which could potentially be more challenging to maintain and test. In essence, code coverage and cyclomatic complexity serve as vital indicators of the software's quality. Code coverage provides insights into the effectiveness of the testing efforts, helping to ensure that all critical parts of the code have been tested. On the other hand, cyclomatic complexity offers a numerical measure of code complexity, enabling developers to identify and address areas of high complexity that could pose challenges in maintenance and testing. These metrics help ensure the testability and maintainability of the software. They allow developers to take a proactive approach in improving the software's quality, leading to more reliable, robust, and user-friendly software products. Lastly, let's look at the Maintainability Index, code review metrics, and customer satisfaction metrics. The Maintainability Index is a composite metric that quantifies the ease of maintaining and modifying software code. It combines factors like complexity, coupling, and size into a single digestible score. The formula, though a bit intimidating, is based on well-established measures like Halstead volume and cyclomatic complexity. When these scores are high, it could be assigned to prioritize these areas for refactoring or improvement. Moving on, we have the code review metrics. These are metrics related to the effectiveness and efficiency of code review processes. Examples include review coverage, which shows the proportion of code that has been reviewed, defect density post-review, signifying the number of defects remaining after a review, and review turnaround time, indicating how quickly reviews are completed. These metrics help evaluate the impact of code reviews on software quality and can identify opportunities to enhance review practices and outcomes. Lastly, we have customer satisfaction metrics. These measure customer satisfaction or feedback regarding software usability, functionality, reliability, and performance. They provide insights into end-user perceptions and preferences and can guide improvements to meet customer needs and expectations. For example, a high number of complaints about a specific feature might indicate the need for an overhaul or redesign, while positive feedback can highlight what's working well. Together, the Maintainability Index, code review metrics, and customer satisfaction metrics offer a comprehensive view of software quality. They allow us to identify and prioritize areas for improvement, enhance our code review processes, and better understand and meet customer needs and expectations. These metrics collectively contribute to enhancing overall software quality and customer satisfaction. Remember, metrics are not just numbers. They are tools that can drive meaningful change and improvement in your software development process. As you can see, software quality metrics play a crucial role in software development. They serve as a guiding compass, directing us towards the areas that need our attention and improvement. By providing quantifiable data, they offer an objective perspective on the software's quality, reliability, and maintainability. We've delved into the depths of defect density, a metric that measures the quality of software code by assessing the frequency of defects relative to its size. This metric helps us understand the number of defects per unit of software, allowing us to gauge and improve the robustness of our code. We've also navigated through the realms of failure rate, mean time to failure, and mean time between failures. These metrics shed light on the reliability and robustness of software products in real-world usage scenarios. They guide us in identifying the frequency and intervals of failures, helping us enhance the system's reliability. Our journey then took us to the territories of code coverage and cyclomatic complexity. Code coverage evaluates the effectiveness of our testing efforts, pointing out the areas of code that need further testing. Cyclomatic complexity, on the other hand, quantifies the structural complexity of our code, making it easier for us to maintain and test the software. We then explored the Maintainability Index, code review metrics, and customer satisfaction metrics. These metrics help us prioritize areas of code for improvement, evaluate the impact of code reviews on software quality, and gauge customer satisfaction, guiding us to create software that meets customer needs and expectations. In essence, these software quality metrics are our allies in the quest for superior software quality. They empower us to make informed decisions, prioritize our efforts, and continually improve our software products. They enable us to not just create software, but to create quality software that meets user needs and expectations. Remember, the goal is not just to create software, but to create quality software that meets user needs and expectations. And that's where software quality metrics come in.